Okay, hello everybody. So today we're going to shift focus from transaction and concurrency and revisit the basis of the relational model. If we go back into the 60s and even in the 70s, predate relational model was the hierarchical model, network model. The birthplace of the relational model, of course, is IBM Research. Codd, who won also a Turing Award for his work of relational model. So that's where it all began. Many of the discoveries and many of the innovation, in database field really comes from IBM Research. I think they continue to be one of the strongest research lab today's. Many, like such as AT&T, Bell Labs, HP Labs, many of these have really reduced in its size and in their scope. But IBM Research continues to be at the forefront of uh, computer science research and continues to be in databases as well. I mean, you can think of relational model just tables like your spreadsheet, but given its simplicity, it's very easy to use. It's very easy to conceive, to think about it, to model your application based on it. And we can see in the last 50 years, there has been a huge success in using relational model and using databases as uh, one of the most important software stack uh, that runs in the enterprise. Basically, any application uh, that you need, who will at some point you need to deal with data. I mean, as we mentioned before, it seems almost impossible to think about a scenario in which there's no data. If there's no data, it's unclear what the application is going to do. So the database plays an important role, and the adoption and the widespread usage of relational model is the testament to that success. And there have been other form of databases, like the recent one, like graph databases or document store, but also in the 90s and there were XML or early 2000. There's XML databases. There were object relation also, and the object relational model is that if you're looking at Java programming or C++, you have the notion of object, but in the database you have rows and columns. And so there is a bit of a mismatch between the object model of the programming language and the relational model of the database. Of course, there are many mappers that kind of automatically maps the two, but in order to be able to support natively uh, the the concept of object, there was also object relational model that was introduced, but it didn't really receive the same uh, widespread usage. I mean, I think there are some object relational model databases around, but they're not that popular. They're not widely used, and relational model continues to be the basis of most database systems. Again, relational databases, just sets of relations. And you can think of your relation as kind of two parts. It has a schema, and the schema defines basically what are the columns, what are the type of the columns. And these are something that you've already implemented even in your else store. I mean, this is the basis of the design or functionality that any database needs to provide. So for example, our schema is a student, bunch of fields, each have also a type. And in terms of terminology, so a relation consists of schema and instance. Instance are the actual records. So a single schema may have multiple instances. For example, if you have a student table, UC Davis and UC Irvine, they both have the same schema, but UC Davis have its own table, have its own instance, while, for example, UC Irvine also have its own instance. So the schema is one component, and the other one is the instance. And the size of the instance, or the number of rows, is also called cardinality. And the number of fields or the number of attributes are called the degree. It's just some basic terminology that you may encounter. In the industry, oftentimes you refer to them schema and table. Instance, it's more on the, I think in the academic literature, you will find the word instance. And then you can think of the relation as just a set of rows, because a set of tuples. And the interesting thing here is that when we talk about the relational model in the context of the relational algebra, by definition, every relation is a set, meaning all the records are unique. But in SQL or in the actual database, the relation doesn't have to be a set. It could be a bag, meaning the relation doesn't have to have a key, or not every row needs to be distinct. But for today conversation, when we talk about relational algebra, we're really going to talk about sets. And then we can think about bags when we talk about the SQL. And example, nothing is surprising. So we have one, the schema is Sid, name, login, age, and this is one instance of this schema. It contains 3 rows. Cardinality is 3 because there are 3 records. The degree is 5 because there are 5 columns, and all the rows are distinct because we're dealing with sets. Any duplicate will just automatically be eliminated. And do all the column in the relation instances have to be distinct? Well, again, as long as each row, the combinations are distinct in terms of satisfying the set condition, that's sufficient. And now, so we have defined our what the relation is, but now the question is, how do we query this? How do we ask questions? And so in NoSQL, we kind of have limited API or limited ability to ask questions. For example, we have gets and sets. So sure, we can create complex program that consists of many read and writes, but the actual language or the API that is supported by the database is just simply get and set. So that's one way, and this is what we're supporting in the ELSER as well. Of course, you also have the range, so there's that one additional support. But the kind of the operator that we support, it determines the expressiveness of the kind of query that can be asked, and also the relation of the representation. So there are 2 things in terms of the kind of query that can be asked: is what is the representation can represent, what can the relational model present, and also what kind of operations that we can define, and based on that operation, which is essentially defines a language. And when we speak any spoken language, whether it's English, what can be expressed in English might be different than what can be expressed in another language. Certain things are easier to express in one language. Certain things is not even possible to express in some languages. So there is a lot of work to formally define the expressiveness power of relational query languages, in particular relational algebra and also SQL. To just kind of give you maybe a little bit more on the linguistic side, for example, the English language is known to be more suitable for scientific. And so it's much easier to express scientific thought in English. Philosophy, for example, German language might be more suitable for philosophy, for example. In terms of poetry, Persian or Farsi and Russian are some of the languages that are really known to be very powerful in poetry. For example, love poetry is known for Persian language. So again, every language have its own unique characteristics. And it's also, the other thing interesting is that if you're talking about just even the way you describe the nature and environment, if we talk about snow, for example, in United States or in North America, you may have 2 or 3 different ways of expressing the quality of the snow. But if you talk in some of the tribes toward the poles, they have about 25 different ways of expressing snow. So certain things we haven't even thought about or conceived of expressing, but a different language or different dialect of that language have the ability and the expressiveness uh, to be able to communicate that. So that the same sort of the linguistic aspect and what can be expressed, what can be presented is also applicable to the database, to the relational query language or to the relational model. And there's another aspect to this is that there's one thing, what is the representation of the data? So that has an expressive power. What kind of relationship can actually be embedded? What kind of relationship can be encoded? And then there's a query language. What statement can be expressed in that query language? And then there is yet another thing is that the result of that query language, what representation is needed to be able to capture that result. And what makes a relational model or the relational algebra is unique is that the same representation that the original data lies in, the answer is also going to be in the relational model. And that allows a very powerful tool because you always, from relational model, you go to a relational model, it allows composability. So again, that's an important behavior of the query language. And so again, that's the power, and also with SQL, it's expressive enough and it's simple enough and it's also declarative enough that you don't really need to think about how you actually solve how do you actually answer the query in sort of you don't have to think about the actual operations necessary. You simply express the type of you simply express what is it what is it that you're looking for, as opposed to procedurally defining every step required. So that's your SQL. The relational algebra, of course, is more procedural in that sense. But this standard, has been one of the most important reason of the adoption. So that means it's much easier, for example, to move your application from one vendor to another vendor. You can now, if you change the vendor, you don't have to go learn how to use this database from scratch because now it has a different query language. So the fact that they all follow the standard, and the standard really began in the 80s, again, that played a crucial role. But if you're kind of looking at some of the uh, more recent databases, the NoSQL, it's just a complete lack of standard. They all have their own interfaces, just so different. You want to, and there's new one coming out, and you have to kind of go and learn its documentation to figure out how that particular system is used. It's just a complete lack of standard. And same thing in blockchain. Not only they have different APIs, they all have different languages. They don't even support the same language, let alone the same kind of functionality or API. So, and that lack of standard, it may give a competitive advantage, but of course, it really limits in the long term the adoption of the technology. Throughout this next 2-3 lectures, we're going to look at a couple of different schemas. One that we're going to use is the student or university database consists of students, courses enrolled. Another one that we're going to use is for sailors and renting a boat. I mean, they're both pretty intuitive, nothing complicated about it. So just some simple example of the query before we kind of really get into the formal definition of these. And this is actually some of it you have already implemented in Alstor as well too. So you can ask a simple question, find all the students of at least 18 years old. And in your Alstor, you have this select function. And if you want to write that in a SQL, very simple structure, you have this keyword select all columns from the name of the table, students table, giving it a name, s, var, sort of this is your condition, where s.age, so we don't have to write students, we simply just use the word s as a shorthand, s.age is equal 18. If I wanted, so this gives me all the students of age 18. If I wanted to say age 18 or greater, well, you will have a greater or equal sign here. The structure of SQL language is pretty straightforward. Of course, now you can, this can It could be over many tables. You could have joins, and from these small building blocks, you can make more and more complex type of queries. And we will look at some of the example of that as well too. Or you could, instead of the select here is selecting everything, we could be more specific, kind of saying select only certain columns. So that's also possible. There's also defining your relation, your schema, all of that can be done in the query language itself too. So for example, the creation of the table of students, this is the syntax. Again, it's pretty straightforward, nothing complicated. You create a student table, you write down all the names of the columns, and you define all the data types. And here's another one. You can create an enroll table. Again, this is of character of size 2. This is character of size 20. And so notice these are all fixed column sizes. So we know exactly this is only 20 bytes. This is 20 bytes. This is 10 bytes. This is, depending on the database, it could be 8 bytes or so forth. And in the real, well, it could be also probably eight bytes as well too, depending on that particular database. But it's a fixed size column. We could have had, for example, an option of variable character, a varchar, and that varchar wouldn't have been a fixed size. And we talked about already is that what, how do you store if you have a fixed size record versus not having a fixed size record. I mean, for LStore, for your current implementation, we're assuming fixed size record, but that is already can be defined precisely in the schema itself. And there's also, same as the LStore, simple APIs to drop table, to alter the table by kind of adding a column. This could be a very expensive operation, especially with the row store. If you actually now need to, if it's a fixed size row and then you need to actually add a new column, you may have to rewrite your whole relationship. In a column store, such as LStore, this might be a much simpler operation because adding a column doesn't affect, because every column is kind of stored on its own. It doesn't really affect any of the existing column. So this could be a much cheaper operation in a column store, depending on the implementation, of course. And again, some basic thing you've already done your assignment is insertion of the new record. So you can insert into the students, you define the columns that you're inserting to, and then you provide the values. And if you don't specify a particular column here, and you don't, of course, you won't provide any value for it. If there's a default value for that column, it will just be generated by the default. So it could be set as null. So you can, so it allows you to only specify the column for which you actually have a value, and it's not the default value. And then again, delete same ways. So you can delete a particular single records or many records if they satisfy a certain condition. Again, we kind of have we have this in your LStore as well too, but we kind of have it with a function API. We're not supporting this query language. Of course, some of the team have also built a UI that they take a query language and then they convert it into the API that we have as sort of as a UI for the project. So, and then there's integrity constraint. And again, this is something we talked about, and this is essential, a core consistency in the asset, the C remains consistency. So that means you define a set of rules and business logic, and these rules, at any point in time, the database needs to fulfill this constraint. And after any transaction is executed, you need to continue fulfilling this or satisfying this constraint. And if not, that transaction cannot be accepted. And oftentimes, these integrity constraints are specified at the time of the creation of the table. Of course, there's functionality of altering a table and adding a condition later on. And these integrity constraints are checked when the relations are modified, or basically when a transaction gets executed, we have to make sure that before we consider that transaction committed is that all the integrity constraints are also satisfied. And we can now formally say a legal instance is one that can satisfy all these ICs. And so that's the consistency of the asset. And a database should only, of course, have legal instances, because otherwise we would say the database goes into an inconsistent state. And why these ICs are important is that you're essentially adding checks to the database. So if you know already certain logic about the of our data, for example, the balance doesn't have to be cannot be less than zero. So all of these rules, all these constraints can be in a formal way and in a systematic way, they can all be embedded into the database, as opposed kind of relying on the application that every time that it does an insert, it makes sure that all these rules are satisfied. And what if there's another insertion happening in the application? Then we have to go back and repeat it. So every time we are making an insert in a different part of the code, we have to kind of iterate through all the constraints and make sure that those are being satisfied. And we also have to go back and forth and keep reading the database to again ensure the validity of this constraint. But it's much more efficiently if they were embedded in the database in terms of managing it, in terms of maintaining it, and also in terms of evaluating it. It will be much more efficient if they are added to the database itself. And the database does provide that facility and at great depth or great length. One example of these constraints is the primary key constraint. Again, something we already also you've seen before, is that if you define a relation key, for example, the student ID is the key, then you cannot have two different students with the same student ID. If you do, then, well, we will violate the key constraint. And a relation doesn't necessarily have to, it has only a single primary key, as we talked about in our, when we talk about indexes and the cluster indexes. So a relation has only one primary key, but it could have other candidate keys that are unique. And for example, the primary key could be the student ID, but every student also has a social security. And well, the social security is also a candidate key and it's unique. No two students have the same social security. So there could be multiple keys. And we can define those constraints saying that when we do insert, we have to make sure that the student ID is unique, but we also have to make sure that the social security is also unique. So that can also be expressed as with the keyword unique. So we can specify which are unique. So just as the sake of an example, if we talk about the student and the course, and if we say, I want to define, let's kind of maybe look at this example first. So we have a create table. We define the char, the student ID, the course ID, the grade, and we specify that the primary key, so that no two record will have the same the same combination of SID and CID. In other words, for a given student and a course, there can be at least one grade. That means the same student cannot retake the same course, because this is unique. If the student were to be able to retake the same course, so let's say the course is 165 and the name is Jim, for example. So Jim took 165 and he has a grade. And we cannot have another insertion into the database, again, Jim taking 165, because Jim 165 is the key of the relation. So adding this primary key, you also kind of imposing this logic that a course cannot be taken twice. So that would be a primary key constraint. Any question? So what is this? So now consider this second table creation. What is it that we are imposing here with these two constraints? What does it, when we say that we have a primary key of SID, what does this mean? How would that translate?
So we could have a student ID that's unique to the student, and then a course ID unique that is unique, and a grade that's unique, right, to that course ID.
So let's do it one at a time. So what does this one, would, what condition this will impose?
That makes it so we don't have more than one row per student ID, right?
Meaning,
Is it that so each student only has one grade per course?
is it one grade per course, or is it each student can only take one course? Because it says again, the SID has to be unique. So can I have John taking 165 and John also taking 155?
No.
Yeah, so that's one condition exactly. So one restriction is that each student can only take one course. Whether this is meaningful or not, that's beside the point. But we're kind of just looking at constraint. So this condition says each student can take one course. Okay, so what does now this one says? So each student can only take one course, and no two students in a course can receive the same grade, because I think you were on the right track. So the CID and the grades are unique. So that means we cannot have in our table, let's say CID is 165 and the grade is 85. So we cannot have 165 with the grade 85 assigned to John and also have 165, the course 165, the grade 85 assigned to Alice. That cannot happen. The grades are unique in each course. So no two students will get the same grade for each course. And also, additionally, each student can only take one course. So the first one, so they kind of add on, they kind of incrementally add upon on. So every time you add a constraint, you adding an additional restriction. So the first restriction is that a student can only take one course. The second restriction is that no two students can get the same grade for the same course, because all the combinations, so SID, the CID, and the grade cannot be repeated. And if they cannot be repeated, that means they can only be assigned a single SID. That means no two students will get the same grade for the same course. Does that make sense? Okay, sounds good. Any other questions? So there's also foreign key and referential integrity. So this basically says the one relation is referencing the key of another relation. It's almost like a pointers. So for example, the SID ID, student ID, is a foreign key referring to the student. So in the enroll table, the SID ID, the student ID is a foreign key because SID ID is the key of the student table. And then we can now define a referential integrity, and essentially that it kind of means no dangling pointer. What that means is that if I have a student Alex in my student table, and if I remove Alex, but this enroll table is still pointing to the Alex, I have to figure out what am I going to do, because this SID ID no longer exists, because if I look up the SID ID in the student table, I'm not going to hit any results. So essentially I get a dangling pointer. And so now so the database will provide several choices of how to deal or how to avoid having these dangling pointer. And of course, we've seen these in HTML. So for example, from one HTML, you kind of link to another. And if the page that you're linking to it's later removed or it's changed its URL, now the page that is pointing, that page that was pointing to it, if you click on it, you get a that link. And so this notion of dangling pointer or dangling references, I think is pretty common in computer science. Again, it's not a new concept. But now the idea is how do we, what are the ways of be able to systematically deal with this issue? So first, in terms of definition, is that we can define our enroll table as before, and we can say that the primary key is SID and CID. So that's the definition of our primary key. That means the student cannot receive. So for this condition, this means the student cannot receive more than one grade for the same course. Or in other words, students can only take each course once because these two has to be unique. We cannot have Alex taking 165 and again Alex taking 165 once more. So you can only take it once. And also further specifying that the SID ID is a foreign key references the student. So the SID ID is from the student table. So we have the enrolled, and so SID ID 53666 points to Jones. And also, again, this record has the same reference ID, again, pointing to Jones. So Jones is taking 3 courses, and all of them are pointing. So, but now if I were to remove Jones, all of these pointers are pointing to nothing. So now we have this situation of the dangling pointer. So, and that's how we refer to this referential integrity. So now asking, what do I do if I remove this? So, and there's generally 3 things you can do. You can say, well, if this is a referential integrity, if there's a referential integrity on the student, and if I were to try to remove this, and in the enroll table, there are already other rows who are pointing to this, then that deletion gets rejected. So I won't allow it. So that deletion is not allowed because already things are pointing to it. That's one condition, one way of kind of dealing with this dangling pointer. Another one is that if I were to delete this, then automatically cascade that delete and go ahead and delete these 3 records that are pointing to it as well too. That could be another choice. And finally is that if I were to delete this, I can go ahead and set these to null as kind of, well, since I removed this, that record no longer exists, so these can be set to null. So these are some of the choices that you often find. Of course, there could be others, different database may provide other alternative to this as well. So either if non-existence, you can reject it, and also kind of you disallow it, or you kind of set a default value to it, and the default usually is null. Again, you've kind of seen this is common in the programming language as well too. And in terms of SQL sort of syntax is no action. Default is no action, meaning that the delete and update will be rejected. Or you can say it's cascade. That means also delete all the tuples that refers to it, as we discussed in that previous example, or just setting it to null. So these are 3 different choices, and that's the sort of the syntax. So you can say, so foreign key is SID, references the student, and on delete cascaded, so anything that is pointing to it gets deleted, and on update set it to default, so kind of setting it to null. So that's basic syntax of how do you define the foreign key, how do you define your referential integrity, and how do you define your regular constraint. And then also for referential integrity, you also need this additional resolution. So beyond just saying, okay, if something is already being pointed to, rejected, there's other choices that can be used. And this is from SQL 92 and 99. So these are all supported. And again, there could be other mechanism here as well too, but that's one set of four different ways of handling it. Any questions?
I've got a quick question.
Sure.
I think I'm just curious, and it might just depend on the implementation for the database system, but do you see circular references, right? Like, will you maybe have something in, the student table refer to the enrolled and something in the enrolled refer to the student? Like, is that typically okay, or do you try to avoid that with this type of system?
So just think about it as objects, and so I think that's the best way to think programming language. In terms of, you can have those circular pointers. You have two different objects, and they're kind of pointing to each other, and that's if it's useful for that particular application, particular scenario that we're trying to model, then it's fine. There's no Here is not so much about, I think, right or wrong here. This is really about, does it reflect the intention, and how do you be able to formally define what action to be taken when you come across these situations. But yeah, so for example, if you had that sort of they're both pointing to one another, that means any rows you delete here may cause a deletion in the other table, and vice versa. And if you have cascading stuff, then you may end up a single deletion may remove all the data in both tables. If this one pointing to one record and that record now pointing to another record and that one's pointing to another record, so you could actually start kind of, I think you could construct a case that your instance is such that it's zigzagging. You delete something and all of a sudden there's a chain reaction of cascading delete and everything could be wiped out. And that's fine. I mean, if that's what the application is, in that particular use case makes sense, then well, then that's the case. So summary, relational model, straightforward, tabular representation, rows and columns. It's very easy, and I think that's the really power of relational model, and that's the really power of the spreadsheet. Spreadsheet is used so widely. In fact, one of the challenge facing relational system, or one challenge of data management even today, is that so much of data in workplace, so much of the scientific data, enormous amount of data continue to just stay in spreadsheet. And so there's much harder to integrate to the rest of the data ecosystem. And because they're so easy and simple to use, although relational systems are simple, easy to use, and it's almost, well, not almost, it's really just like a spreadsheet, but spreadsheets are even more easier to use. And so that's why a lot of data gets trapped in the spreadsheet. And so there's a lot of interesting integration problem of how do you take spreadsheet data and integrate it and perhaps bring it to relational, especially in the scientific domain. Often researchers and scientists, they just want to focus on the experiment that they're running and the data that they're collecting, and they use the quickest and most ad hoc way of just capturing that data so they can move on and find the next set of exciting data. So that's in the scientific domain, that's one of the main challenge. Of course, once you want to run statistics on it, want to run analysis on it, then they probably still have to integrate it to a more a different form, unless they continue using that CSV files or the spreadsheet, the most common way of storing their experimental data. And again, we talked about the rules, integrity constraints. So to define what is a valid instance, what is a valid set of records, and to make sure that the data remains correct in accordance to the logic of the application and the domain that we are dealing with. And well, query languages are very powerful, and we will now, next step is to really go in depth in the query language itself and see and do kind of examples, walk through examples, see the type of query that can be expressed and answered.